Okay, so we've made it through the first half of our journey. Kind of exciting. Okay. So here's kind of where we're at right now. So we figured out this major concept of the mole. We figured out how to do chemistry, scientific notation, density, mole conversions, molarity, all that good stuff. And we kind of started into the heart and soul of it, which is that concept of like Coulombic attractions and how do atoms interact. And so that's fundamentally what the rest of the term is going to be. Is that how do we explain the willingness of atoms to bond together, okay? And so that's the basic idea. So if this first kind of short video that we're going to watch today, it isn't very long, but it's kind of cool because it explains how Mendeleev began to organize the elements. So you kind of got a vision, and you got to keep straight the terminology. So when we're talking about an element, and again, that when they had the word atom, atom comes from the Greek word at the time, it still does, means indivisible. So basically they said, okay, if you take water, for example, okay, I can take water and I can separate that into oxygen and hydrogen. Pass an electric current through it, I can separate it into oxygen and hydrogen. Okay, cool. So, but I can't take oxygen and hydrogen and separate those down even further, okay? So once I get those oxygen and hydrogen particles separated, I can't divide them any further. So if you look at like DNA, okay, DNA is nitrogen, oxygen, hydrogen, a whole bunch of different things that make up DNA. So we can separate DNA, if here's your biology connection, okay? So we can separate that into its constituent parts. So when Mendeleev was doing his work, you have to understand what they knew and what they didn't know. So at the time, they knew like the relative atomic mass, okay? So that's going to be important. They knew how it would react with different elements, okay? They knew some ratios in terms of how it would react. Like, for example, they might know that hydrogen and oxygen combine to water to produce in a ratio of 2 to 1. This is H2O. They had an idea of melting and boiling points. They knew which substances were gases at room temperatures, and they knew which ones were metals, and they knew which ones were liquids. So they had some ideas of physical properties. And so what you all are going to do is very similar to what Mendeleev did. So you're going to take, eventually today, and you're going to cut out these little pieces of paper, okay? And you're going to say, okay, for example, atomic mass, 1, 19, 36, 16, okay? Melting point, boiling point, O and oxide, which that means how, in what combination does this thing react with other compounds? How does it react with chlorines, okay? So he basically literally like cut these out, and then he began to arrange them based upon these properties. And so the genius of what Mendeleev did is that he knew that there should be some elements that could fill in the gaps. So he actually left gaps, and he said, okay, at some point we should find these elements that fill these in. The other thing that he did not know at that time, and wasn't until hundreds of years later, was the concept of electrons and protons and neutrons, okay? They didn't know those particles existed. So when he was arranging them, we didn't know knowledge of S sublevels and P sublevels and how those sublevels interact and why chlorine has 7 valence electrons and why that wants to gain an electron. Didn't know any of that. So he could basically arrange these things based solely upon those properties. So we'll give this a quick watch. It doesn't take very long.
recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behave. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium, after gold, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time. Scandium, germanium, rhenium. The element he called ekamanganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitry predicted its existence, 30 years after he died. Dmitry died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitry Mendeleev, the architect of the periodic table, will be staring back.
Okay. So what you're going to do today, as best we can simulate it, is try and replicate what Mendeleev did. Okay? So on this piece of paper, so you're going to have, and it's kind of arts and crafts day. So you're going to cut out a square, and you're going to have atomic mass, which is 1, like in this one, melting point, negative 259, boiling point, negative 252, O in oxide, 0.5, and then Cl in chloride, 1. Okay? So this is what you're going to do. So what you're going to do, first thing I'm going to cut these out. And then I'm going to give you in the back a bigger sheet of paper. And then you're going to have this. So let's talk about what each one of these means. So atomic mass, you know what that is. That's based upon hydrogen. Okay? So since this has a relative atomic mass of 1, which element do you think this might be? Hydrogen. Okay? Hydrogen, right? Now, so let's talk about the melting point. Okay? So the melting point is negative 259 degrees Celsius. Okay? Why do you know that that's not a temperature in Kelvin? Because what?
It's negative.
It's negative. 0 is as low as you can go in Kelvin. Okay, that's absolute 0. So I know this scale isn't in Kelvin. So you're at minus 259. So if you're below negative 259, what phase is that thing going to be in? Solid, liquid, or gas? Well, think about this. What's the melting point of water in Celsius? Dear Lord.
32.
No, in Celsius. 0, right? So the melting point of water, so let's make sure everybody's cool with what this means. So the melting point of water is 0 degrees Celsius. So if you're below 0, what phase are you going to be in?
Solid.
If you're at minus 5, right? Wouldn't that put you as a solid, right? So if you hit 0, that's when you're going through that phase between solid and liquid, right? So what's the boiling point of water?
32 degrees Celsius.
100 degrees Celsius, right? So if you're somewhere between the melting point and the boiling point, what phase are you going to be in?
Liquid.
Alec Grill.
Liquid.
You're going to be in a liquid, okay? So if you're above 100 degrees, what's that going to be in? It's gas, right?
Oil.
Okay? Vapor, whatever you want to put it. So here's the deal. So right now, if you look at this, so if you wanted to have solid hydrogen, you would have to be below negative 259. Okay? So notice that this only has a very small range of temperatures where this thing is a liquid. It's only a liquid between negative 259 and negative 252. So that's only a 7-degree swing. Okay? Water has a 100-degree swing. Okay? When it's a liquid. Right? So this is a very small point. Now, room temperature right now is about 20 degrees Celsius. So since we're well above that boiling point, what phase is hydrogen in right now? It's a gas, right? Okay, it's a gas because we're well above that boiling point. So if you want to get an idea of something as a solid, liquid, or a gas, okay, look at that. So like this one here where it has atomic mass of 23, it has a boiling point of 889, okay? So you'd have to be above 889 to have that thing as a gas, which would be really, really hot, okay? The melting point is 97 degrees Celsius, okay? So since that melting point is 97, here's what I want you to think. So one of these elements has a melting point of 97 degrees Celsius, okay? has a melting point of 97 degrees Celsius. So this is what I want you to think through. At 97 degrees Celsius, okay, at 97 degrees Celsius, we're at about 20 degrees, okay? So would this substance be a solid, liquid, or a gas at room temperature? Ramen. You can consult.
Sorry, I was spaced out, like I always am.
Ella, unspace your friend.
Liquid. Solid. I knew it. Solid.
You were just seeing if I knew the answer?
Yeah.
Okay.
Testing.
Okay. So this is going to be a solid because of the fact that we're below the melting point. So anything that has a melting point basically above 20 degrees, okay, that means it's going to be a solid here, right? So those are going to kind of be the most, so none of these will tell you exactly that it's a solid, liquid, or a gas. It's just going to tell you what the boiling point. Now, on some of these where it says like the O in oxide and Cl and chloride, what that's referring to are how well these combine with different elements, okay? So some of these just have dashes, okay? So what that means is that that particular substance isn't going to bond with anything, okay? So it won't bond with chlorine and it won't bond with oxygen. That's basically what that's telling you. So you're going to have that, and then you're going to have this sheet, and it says list the 4 elements found on the periodic arrangement, okay? So you can either glue them or you can take tape or whatever. So let me go get a big piece of paper. I'll show you what that's actually going to look like. Okay. So you're going to have these bits of paper cut out, okay? And then I'm going to give you a big piece of paper like this, and you can then glue them or however you want to. But the idea being is that you're going to group these based upon certain properties, okay? And you can, and there's going to be 4 of them, okay, that you can group them on. It's up to you. But what you want to do, and this is the whole idea of Mendeleev, is that you're trying to figure out this pattern. Now, when you get done with this, now this is going to require a little bit of thought, okay, just a little bit. On the back side here, you're going to have this big graph paper. What?
I said your pen.
I know. How I hate these. Let me count the ways. Maybe you took the weekend off.
I think we should take what was your Wi-Fi? Oh no, just use the good old whiteboard. Too fun to be stressed.
Well, now it decides to write. Okay. So, anyway, now that you have this. So, here's, this graph is going to require a little bit of thought.
Oh god.
So, on the x-axis, you're going to put atomic number. One through 20, okay? Then, on this, then select either the melting point on the label the y-axis, okay? And then you say, so here's the deal. So you're going to put melting point on one, and it kind of tells you how to lay that out. Then, when you do that, what you're gonna do is you're gonna basically get this graph, and it should look fairly linear. So you're gonna put that on the right side, I'm sorry, this actually goes on the right side. And then, on the left side, then you're going to put the formula for oxides, label the y-axis, chlorine or oxygen atom as follows on the left y-axis. So this is what's going to get a little bit confusing. So this is going to be your chlorides. So you're going to have atomic number here, and you're going to have melting point over here. So what's going to be common is your atomic number 1 through 20. So you're going to go like atomic number 1, and you're going to come over here, and you're going to plot a point based upon this axis, and then you're going to have atomic number 1, and then you're going to plot this information. So you're going to have two different lines on the same graph. So for atomic number 1, you're going to have two different points. For atomic number 20, you're going to have two different points. So on this graph, you're going to have two different lines. And the reason that we do this is because that allows us to look at two bits of information on the exact same graph, okay? That's what that is for. Okay, so here's what you want to do. I got a tub of scissors back there, so stop that for a second.
Yep.
Okay, so here's what you got. You're going to take this big sheet of paper. You're going to, first thing you'll do, I've got a tub of scissors back there, and you're going to cut these out, okay? So they're pretty limited, you can just go like that. And you don't have to cut exactly like on the black line unless you really want to, okay? So, and then I'm going to have like glue sticks or tape or whatever. Glue sticks might be a little bit dried out, so it might just be easier to use tape. And so, again, you kind of have to, the whole idea of this exercise is that you put yourself in the mindset of Mendeleev, okay? Again, you don't know anything about electrons, protons, Schrodinger's equations that describe probability of wave functions, nothing, okay? The only thing you have are these. So the idea being is that you're going to look at this and say, okay, what are some characteristics that I can look at, and how can I arrange these? And you might have to leave gaps, okay? And that's kind of like what Mendeleev did. So if you look at these atomic numbers, you've got 1, 9, 7, 39, 28, 24, 72, okay? You've got you don't have all 72 of these elements, okay? You don't. At the time, Mendeleev did, okay? But he said, hey, you know, we don't know everything yet, but I'm going to leave some gaps where I think these are going to be. So I'll tell you right now, don't try and arrange them just in sequential order of atomic mass. 1, 2, 3, 4, 5, okay? It's not going to work. You've got to look at how you can group these elements. Now, I'll get out the colored pencils. It's strictly optional if you want to color them. So if you want to group all of the ones that have chlorides of 3, so you have Cl and chloride, those are 3. If you want to color those a particular color, hey, great, okay? If you want to color if you want to go through and sort them and go, hey, I'm going to color all of the solids at room temperature a particular color. I'm going to color all the gases at room temperature a particular color. Okay, that's cool. Even if you just want to like put hashing, like kind of like shade it just a little bit, so you say, oh, okay, because that might make it easier to reference when you go to put that. So that might be one of those deals. You put in a little effort up front. Say, okay, hey, I'm gonna color at least all of the solids a particular color. I want to put all of the gases a particular color. Okay, that might help you out in that regard. Okay, I'm done. Let's go do science.